All right, welcome everyone to this week's Proof Theory seminar. I'm delighted to welcome Alexis Saurin, who will be the speaker for today. And he's going to be speaking, so Alexis Saurin is a CNRS researcher based in Paris. And today he'll be speaking about, well, actually a project of work that he's been embarking on for quite a while now, based on non-well-founded reasoning. So proof structures which have circles or loops in them. And in particular, their relation to computer programs via the Curry-Howard correspondence. So I'm very excited to see what he's got to say today. So Alexis, the floor is yours. Please take it away.
Thanks, Anupan, and thanks a lot to all the organizers. It's a great occasion to speak here. Yes, indeed, I will tell you about how we can make circles in proof and avoid vicious circles, like turning potential vicious circle into virtuous ones. So let me start with some introduction, some background. So most of this talk will deal with logic with least and greatest fixed points, which model inductive and co-inductive reasoning. So they are useful to encode, of course, these inductive and co-inductive reasoning and data structure. But their proof theory is still underdeveloped. And like there are current trends in several labs in pushing those non-well-founded and circular reasoning. It's also like circular or cyclic reasoning. I'm using usually this circular terminology, but that's not that's not shared by everyone. I will tell you maybe why I'm keeping this circular terminology. My specific focus here will be not only on expressing statements and understanding which statement can be derived, but also the structure of the proof system itself and of the proofs, especially because we want to use this proof system to study their computational content and how we can extract some information on what can be computed with those proofs. So this work will be mainly considering linear logic extended with least and greatest fixed points. First, I will tell you about the proofs when proofs are finite trees, including some induction rule, and then we'll turn to the case with proofs being infinite trees, having non-well-founded branches. I hope to convey some of the main results on the structural proof theory, especially focusing on the various cut elimination results for those logics. So a particular interest will be on the circular fragment of those non-well-founded proofs, those where infinite trees are regular trees and have a finite representation as a tree with back edges. And the long-term goal is to extend the proof program correspondence to recursive and co-recursive programming with co-inductive data types, especially with a target toward proof assistance. So we have a project starting in France with several colleagues funded by ANR. So I will just use this occasion also to promote it for a second. So involving people in Nantes, Lyon, Marseille, and Paris. Especially because we will be hiring several postdocs in the coming years, and a PhD grant will be offered in Marseille starting next academic year. So like if you know people are interested, like please you can contact me on this matter. So the outline of the talk will be the following. So after pursuing this introduction, I will turn to μMALL infinite, which is the circular, containing the circular and the non-well-founded proofs. Then we will focus on the fragment of this logic, looking for the cut elimination proof for the multiplicative additive fragment of linear logic with fixed points. So this is a joint work with David Bald and Amina Douman. And then I will show you, I will tell you about a new result on extending these cut elimination results to full μMALL and some consequences. of this two more non-well-founded proof that what we'll have in the first section of this talk, by relaxing some condition we need to impose on the derivation, the non-well-founded derivation, to have soundness of the logic. So this is a joint work with David Bald, Amina Duban again, and Denis Kupperberg. And finally, I'll tell you about the work with Abhishek, who's here, and Luc Pellissier on proof nets for non-well-founded proofs. So trying to understand how we can find a balance between some very sequential aspects of sequent calculus and some inherently parallel aspects of non-well-founded proof and the validity criteria of non-well-founded proofs. Okay, so then to continue introducing and motivating, let's just take for a moment a look at this famous and very basic Narszatarski fixed point theorem, which tells us that like a monotonic operator on a complete lattice has a least and a greatest fixed points. And those fixed points are characterized respectively as a least prefix points and the greatest prefix points. And this characterization in terms of least prefix point and greatest prefix points gives us means to reason by induction and by co-induction. Okay, and from those this result we can infer potential inference rules for managing fixed point operator to be introduced formally. Okay, so the mu xf will be the construction of a least fixed point statements in our logic. Again, we have a right and a left introduction rule. And in the co-inductive case, for the greatest fixed point, like we have some dual rules, as often in sequent calculus, we have very symmetric rules. So the new left rule mimics the mu right rule, and similarly with mu right and mu left. Okay, which are below the other one. But these logic expressing a fixed point in terms of mu and nu operators are not the only way to deal with induction and co-induction. And a very fruitful approach is that of Martin-Löf inductive definition. So let me tell you some words about LKID and how we introduce inductive reasoning with this, in this logic. So the idea is to have a set of inductive predicates described with their production rules, like as here we have P, which is an inductive predicate, which have several having several production rules. It may depend on some non-inductive predicate and some other inductive predicates. So in particular, we can have mutual dependency of inductive predicates. So some example is typically this production rule for the NAT predicate, okay, expressing that some term represents a natural number. And from those production rule, we can extract a sequent calculus, which is sequent calculus for classical logic extended with rules inferences for the inductively defined predicates. So on the right, it's simply the use of the, let's say, the production rule instantiated with some term on having the appropriate structure. And on the left, it's the induction reasoning containing the use of the induction hypothesis. So as I told you, it's possible to have mutual dependency. So typically here with predicate for even and odd numbers, which are mutually dependent. And then when we generate the proof system associated to it, of course, we'll have an induction hypothesis reflecting this mutual dependency. So in this setting, we can, for instance, have those inductive definition, which should be stated as a production rule. So here, typically, NAT would have, as you saw in the previous slide, you have two production rules corresponding to this disjunction the left projection rule corresponds to the case where x is equal to 0, and the right one corresponds to the successor case. But we can express a list of a natural number, and if we were to extend this system with co-induction definition, we could express, for instance, streams of knots. And like, of course, the proof system would need to be extended, and actually it's complicated to deal with both induction and co-induction in those proof system with inductive definition. But those predicates could be reformulated, okay, saying that essentially if NAT is an inductive definition, then it should be a least fixed point of the predicate transform. Okay, so it should be viewed as the least fixed point construction on an operator taking a predicate n and returning this one. And we can do this for both the NAT, the least NAT, and the stream NAT predicates. And we can, of course, forget about the first order part of the statement and look at the propositional skeleton of those statements. And here we find a propositional mu calculus formula. In the rest of the talk, I will be only propositional and stay in this fragment where we have this variance of the mu calculus, especially linear logic extension of the mu calculus. So expressing both least and greatest fixed points gives us the ability to consider interleavings of least and greatest fixed points, and that's important in terms of expressiveness. Especially, we can express, for instance, some fairness property. So now, if we have, so we want to design a mu calculus for multiplicative additive linear logic at first, and then we'll allow infinite derivations. So this first logic of study was introduced by David Bald and Dale Miller. So it's the grammar for formulas. The first two lines is simply the grammar of multiplicative additive linear logic. So I will just recall it so for everyone. So we have atoms and duals, I mean a negation of atoms. We have 4 units, which is due to the fact that conjunction and disjunction in linear logic are split in 2 versions of logical connectives due to the absence of the control on structural rules. So we have this par connective, which is corresponds to the classical disjunction, and this plus connective here corresponding to the intuitionistic disjunction. And we have 2 conjunctions, the with here, which is the additive conjunction, and the tensor, which is the multiplicative one. And they correspond to like usual inferences we have in LK that are in the presence of structural rule, they are interderivable. But since in linear logic, we will control the use of structural rule, they won't be interderivable anymore. And that's why we split those in 2 connectives. And we extend this logic with fixed point variables and the construction of a least fixed point formula and a greatest fixed point formula. So mu and nu here are binders, which bind x in F, 3 occurrences of x in F. As usual in linear logic, negation is involutive, and it's not a logical connective. It's an involutive operator on formula. And on mu and nu, it extends this duality. And for instance, the formula, the dual of the negation of the formula mu x, x tensor x, will be mu x, x par x. And notice that here, we do not introduce any mention of a negation on those fixed point variable. That's the way we should formulate negation here. And we'll work with one-sided sequence. That is, sequence are just lists of formula. This is due to the involutive negation. So we can do this as we can do in LK. And from time to time, I will still write examples with 2-sided sequence, but you should view it as a short for the sequence containing the dual of the formulas in gamma comma, the formulas in delta. But it will be, it will make the example more readable, and especially from a computational perspective. So like the previous formula we mentioned, we can encode them in this logic. And the point is to consider what the proof of those formula will look like, and whether we can represent some data structure and some computation with those proofs. So mMALL sequent calculus is on the first line is just mMALL sequent calculus, and in the last two lines I have the inference rule I showed you in the slide on Knasted ASCII, with a slight variant for the new rule that is necessary to get a cut elimination result. And as usual in sequent calculus, but it's even if it's not always depicted in detail, a crucial point in the sequent calculus is to have an ancestor relation, okay, between formulas in the conclusion and formula in the premises of sequence. So here I make it explicit, okay. That's especially telling us that this occurrence, the side occurrence of the auxiliary occurrence of X in the left premise is an ancestor of F with G in the with rule, and the G occurrence in the right premise is an ancestor of F with G, and each formula in gamma is an ancestor in the left or right premise in the ancestor of the formula in gamma at the same position in the conclusion. So we can do this for every inference, and that's actually essential to design cut elimination procedure which are meaningful computationally and which do not equate all proofs, especially. And with this sequent calculus, we have a cut elimination theorem proved by in the PhD thesis of David Bald. So we are happy. We have a nice logic. It features some issues. So especially in the cut elimination, since the new essentially breaks the cut formula property. If you look at the new rule here, in the premises, I have this formula S and its dual, which have nothing to do with the conclusion formula. We break the subformula property. So of course, if I get a cut-free proof of mMALL, which do not refer to the new connective, since all the other connective have the subformula property, or sort of, because for this mu, we will come back to this notion of subformula induced by this rule. We would get some subformula, but the new is faulty. And if we prove a statement about a co-inductive formula, a greater 6-point formula, then we lose the subformula property. And we have other nice proof theoretical results like focalization and this. So one of the motivation is in particular to restore the subformula property and to study what we like to try to simplify the inference rule and the reading on the inference rule, and also the dynamic of the cut elimination, because the key case of the mu and nu rule in mMALL is quite complex, and its computational meaning is not that immediate to understand, and it will be made much more simple in the non-wellfounded setting. Of course, there's a price to pay, which is that with non-wellfounded derivation, we will need a global correctness criterion and proofs. So that's a good part of what I will be telling you now. So how to now design an extension of linear logic with least and greatest 6-point and non-wellfounded derivation trees, circular non-wellfounded derivation trees. So this is actually not a very recent idea. Like already in Euclid's Elements, you have a reasoning by infinite descent, okay? And in this, essentially in this proof, what Euclid does is he suggests a pattern of a proof construction that would be an infinite proof pattern, okay, that would result in a contradiction. And that's the use of infinite descent with inductive data structures. So, and especially this is used in arithmetics. So you can use infinite descent negatively, so to derive contradiction or negative statements. So that's essentially how we find them in mathematics usually. But in computer science, there are also a lot of use of co-inductive predicates. And in that case, we can derive, we can build a notion of infinite and non-wellfounded derivation, which derive positive statements. Let's say, for instance, with a simulation predicate, we could build such an infinite derivation tree, which has one, the rightmost branch being infinite. And this one will be considered as valid because on this infinite branch, the co-inductive predicate sim is considered principal infinitely often. Okay, we unfold sim here, we will unfold it here, and we will unfold it infinitely often on this branch. That's so here we have on the bottom part an infinite derivation that will be valid because the co-inductive is derived on the right infinitely often. And on top of the slide, with this even and not predicates, this infinite derivation will be considered valid because the even predicate on the left is derived infinitely often. The not predicate is also principal infinitely often on this branch, but it does not contribute to the validity of the derivation. Okay, so this slide is just to review a bit of the use of circular proof in the literature. So they appeared early in like Tableau methods for the mu calculus, for the model mu calculus in work especially by Walukiewicz, for instance. But they were rarely used for as proof program objects, like for the extending the Curry-Howard correspondence. And especially they were not used in a very structural proof theoretic way. Recently, lots of work were done on circular or cyclic proof systems, and I just mentioned some of them, and especially like the work by Bahare and Graham, and Anupam, of course, with several people. Here I mentioned Amina and Damien, but he has lots of other contribution. And Lyron and Robin also have made some development on cyclic proof for transitive closure logic, for instance. So what would this non-well-founded proof system look like for a mu calculus? So take your favorite logic L, okay, add fixed point combinators as we did for mMALL, and we will consider pre-proofs, which are trees co-inductively generated using the inference rule of your proof system and inferences for mu and nu. But now the rules won't be anymore exactly the one we had in the case of mMALL. We can use simpler rules for the mu left introduction and the mu right introduction. In that case, all the introduction rules will be just fixed points unfolding. Okay, in the conclusion, you have a fixed point. In the premise, you have the unfolding of the fixed point, like f, where 3 occurrences of x are replaced by the fixed point formula. So those 4 inferences are built in this way. And of course, you can easily imagine that there will be an issue if we do this. First, we do not make any difference between least and greatest fixed points. So that's a problem. And since we can build co-inductive non-well-founded derivation trees, then we can derive actually any formula in essentially whatever logic you consider. Okay, we can build a pre-proof which unfolds this mu xx formula in itself infinitely often. So we have an infinite derivation of mu xx. And by unfolding the mu xx infinitely often, you can derive mu xx comma f for any formula f. And with a cut rule, you can derive f. So any formula can be derived with a non-well-founded derivation. So we have to tame them in order to restore, to make them into a soundproof system. So of particular interest here will be those non-well-founded derivations which have only finitely many distinct subtrees, subderivation trees. So that we call circular. So it's essentially the regular fragment of the infinite trees of pre-proofs. So just a word about this circular mention is that in the linear logic community, the cyclic terminology was already used for a class of logics where the rules of exchange is restricted. So we have like, let's say, already some notion of cyclic derivation in linear logic, and that's why Luigi Santocanali coined this circular name when coming up with circular proofs for additive linear logic, purely additive with no multiplicative. So in particular, like my favorite logic is linear logic. So I want to consider this instantiated with linear logic, and with one-sided sequence, we don't have to consider the left rules. So this is a μMALL infinite sequence calculus, the inference rule. So the first 3 lines are just what we saw. I mean, it's still mALL. The last 2 lines are the new fixed point rules. And in the 4th line, we have the rules for the exponential modalities of linear logic, which allows us to control the use of structural rules. Weakening and contraction will be available only on formulas tagged with a question mark. So they are freely available on those formulas, but not in general. The only structural rule we have is still the exchange. And we have an introduction rule for the question mark formula, and the promotion rule introducing the bound under the assumption that the context is made of only question mark formula. Again, the ancestor relation I showed you before, which now will be crucial because it will be used to restore the soundness of the proof system and define the validity condition. But if we reconsider this proof system now, apart from the cut, all the rules look like they satisfy the subformula property, except that for the new and new rules, we have the fixed point unfolding case. So on the top, it's not a subformula of the bottom formula. But we can define a notion, I mean, actually, there is a classic notion in the literature of Fisher-Ladner subformula, which is like this. You just take the usual notion of subformula, but for fixed point formula, you consider that the unfolding in the set of subformula. And actually, it's an appropriate notion of subformula in the sense that we have only finitely many such formulas for any f. So here, just an example. So for this formula, the Fisher-Ladner set of subformula is made of f, the unfolding of f, the 2 subformulas of the tensor, the 2 subformulas of the par, A and A perp, and the right subformula of mu y f. But we need also the left subformula of the tensor, but it's already here because it was f. And we need also the unfolding of the mu y f formula. But since f is closed, y has no occurrence, and its unfolding is simply f. So we have already this in our set. So we have the full set of Fisher-Ladner subformula, and we can use this as such a graph with potential loops. Okay, and in this graph we can make, of course, infinite paths when we have such loops, and the shape of those paths will be crucial for the notion of validity we want to study. And notice here that each time you move up in the graph, okay, if you look at the formula f as the root of the graph, the top node of the graph, okay, you go down in the graph till you find some occurrence of f, and you move back to f. But this is only possible if f was a fixed point formula. In particular, that means that if you make an infinite path in such a Fisher-Ladner graph, the topmost formula in the graph that you can encounter infinitely often will be a fixed point formula. So it's either a mu formula or a new formula, but there's no other possibility. And look also that if I consider a strongly connected subset of this graph, there is one formula that is minimal for the regular subformula notion. For instance, the set of these 3 subformula f, the tensor formula here, and this tensor formula there is strongly connected. Okay, I can reach any of them, any pair of formula, and F is the subformula of the three formulas. And again, if I can add to this set mu YF, it's still a strongly connected set subset subgraph. And F is again the minimal formula for the regular subformula notion. And in this case, it will be a greatest fixed point. So essentially here you have the basis of our correctness criterion. We will look for some such non-well-founded derivation. So here this is regular, meaning like those back edges mean that the proof rooted here is the same as the one we had from the bottom, and the same for this, for the proof rooted in F. And I want to say that a proof will be valid if some condition holds for infinite branches of this proof. And I will say that a thread on an infinite branch, okay, an infinite branch will be like an infinite branch here labeled with sequence, okay, is an infinite sequence of formula occurrences, Fi starting from k, from some integer k, so not necessarily from 0, such that every Fi is an element of gamma I. So as a formula occurrence, that means it's a position, some position in gamma I. Okay. And Fi plus 1 is the immediate ancestor of Fi for the relation we saw in the proof system. So this is what is a thread. And the thread will be said to be valid essentially if it unfolds infinitely many news. So that's a bit too weak to state it this way. And more precisely, what we need to say is that the condition to be valid is that the minimal formula which occurs infinitely often on a thread shall be a new formula. And that's this is essentially what I showed you on the previous slide for Fisher-Ladner subformulas. The proof will be said to be valid if every infinite branch contains a valid thread. And for this notion of validity, first, the circular fragment, the validity of circular fragment is decidable and p-space complete actually. The non-well-founded fragment has a soundness property with respect to some truth semantics, the usual truth semantics of the new calculus, and it admits cut elimination. So just to give you an example of what those circular proofs look like and what we could compute with them, on the left here. So if I represent the natural number with this formula, mu x 1 plus x, which is the same as the beginning of the talk, I can represent the 0 integer with this proof, which unfolds the least fixed point, takes the left disjunct, and then this is one of the truth unit of linear logic. I have this in France to close my proof. This represents 0. This represents the successor, okay, k plus 1 when I have a proof of k. And this proof computes the double function that is shown above. Okay, if I cut, and actually if I cut double with any proof pi k, and I eliminate my cuts in with the strategy we'll see, my result will be pi k plus 1. But this can be done also with co-inductive statements. So this formula representing streams of natural numbers. Okay, so if pi sux represents the successor function, I have here a proof that will enumerate every natural number and build a stream of every natural number from starting from its input. So here I'm using the bank of linear logic to allow me to make this contraction and the weakening here, and I will discuss this after reviewing the cut elimination result from mMALL. Okay, so finitary proofs, the one from mMALL, can be embedded in the circular proof fragments here as valid proofs, but the converse is an open problem for μL. Even if we know this for inductive definition, it's open for μcalculi with linear logic. So let's go to mMALL cut elimination.
Alexis?
Yes.
Just let you know, you've got about maybe 15 minutes left. I don't know if you're on
yes.
pace or not. Okay.
Okay, fine.
Very
Thanks a
good.
lot. Yeah, I have some appendix slides, so I don't
Okay.
have 57
Good.
slides. But I need to hurry a little bit. Okay, so let me tell you about cut elimination. So since we have infinite derivation, what we'll be considering are potentially infinite cut reduction sequences, and we want a notion of convergence, so which is just the usual convergence for the tree topology. Our strategy will be to push cuts up from the cut and so that to dig them deep in the tree, in the proof tree, where they have the lowest weight possible, and therefore we can have convergence. So in our cut elimination strategy, now we may have just a little issue with some rules about the cut commutation. Okay. Because on an infinite branch, we might encounter infinitely many cuts. So we consider a generalized cut rule, okay, which is somehow a subtree of finitely many cuts. So we eliminate actually those multi-cut rules from our proof system. So the cut elimination relation is made of cut commutation rules, okay, where one of the premise of a cut is an auxiliary formula, is not a cut formula. In each case, I can commute the cut up the inference rule. And then those rules are productive in the sense that the cut gets deeper. But the key cases of cut elimination, the internal phase of cut elimination, is not productive because the multi-cut will remain at the same depth in my tree. So we have to ensure essentially that this infinite phase cannot go on forever. So the cut elimination procedure goes by performing internal step when we cannot do something else, and perform a cut commutation each time we have this option. And we also want to make it in a fair way, that is, every external commutation rule that is made available at some point should be performed. The result we have is that the internal phase always halts, and cut elimination produces therefore a pre-proof, but well, not necessarily a valid proof object, and that actually this pre-proof is valid. So we do not lose threads, valid threads, during the cut elimination. But also a side observation is that the circular fragment is not stable by cut elimination. So we don't have cut admissibility for circular proof, but from a curry-word perspective, that's actually a good point in terms of expressiveness. Because if I want to eliminate the cut on my enum proof, pi enum I showed you before, from like if I cut it with 0, surely I would expect this to produce the stream of natural numbers, the cut-free proof containing all natural numbers, which cannot be circular. Okay, so a few words about the extension with μMALL. So the proof goes by actually simply encoding the exponential in μMALL. Okay, so there is a natural encoding of question mark and bound in μMALL. So the question mark is encoded with the least fixed points. And if you read this is a like view it as the intrinsic disjunction if you're not very familiar with linear logic. So this is a formula that will give you the opportunity to make finitely many times, either to reach formula F, or to reach this bottom formula that can be weakened, or to duplicate your formula, which will give you the possibility to make a contraction. And this is the classical, corresponding to the classical disjunction. And for the bound, this is encoded with the dual formula, and it's the greatest fixed point. And somehow this will have the behavior of the promotion, in the sense that it will be able to react to any finite number of structural rule ending up possibly with the use, and then the proof goes mMALL infinite with this encoding, simulating the cut reduction sequence in mMALL, and finally applying the mMALL cut elimination theorem. So this is just a slide showing how the exponential rule of μLL can be derived in mMALL infinite. And for the promotion, you can see that we need to use a circular proof to encode the promotion. But we have a property of preservation of validity in the sense that if pi is a valid μLL infinite proof of gamma, then its translation is a valid mMALL proof of the encoded sequence. And this is an if and only if statement, which will be important. And then every cut elimination step can be simulated, but we have to be careful about the promotion, because the promotion, since it contains circularity, okay, some packages, it may involve infinite reduction. And indeed, the simulation of the promotion commutation rule can be performed with an infinite reduction, an infinite converging reduction. So every step of the cut elimination commutation steps or key steps can be done with finite reductions, but for the promotion case. And also, when you want to encode reduction steps that occurs above a promotion, because this corresponds to eliminating a cut in infinitely many copies of the cut. But that won't be an issue to get a cut elimination, because we can prove that if we map a fair cut elimination reduction sequence from μLL to mMALL, then we can't ensure that it is an omega indexed sequence. It will be a transfinite reduction sequence. But this transfinite reduction sequence will have a very strong notion of convergence, which is actually known as strong convergence in infinitary rewriting. And to this strong converging sequence, we have a compression lemma that tells us that there exists always an omega indexed reduction sequence which converges to the same limits. So we can move, we can obtain an omega indexed reduction sequence which is still fair, and therefore we can apply mMALL cut elimination results to obtain the validity, the cut freeness, and the validity of the limit of the reduction row, which is actually the encoding of the limit of sigma. And therefore we can get validity and cut freeness of pi prime. So these cut elimination results actually also give us as a corollary cut elimination for the natural statement of μLK, non-wellfounded μLK and non-wellfounded μLJ. Through so for the intuitionistic case, through usual embeddings of intuitionistic into intuitionistic linear logic, but you have to consider the call by value. There are several such embeddings, but you have to take a particular one, the call by value, because this one does not introduce cuts. The call by name would introduce cuts and it would break validity. So we wouldn't have the validity preservation property I used before. And for classical logic, it's a little trickier because the standard translation in the literature, the T and Q translation, introduce cuts and therefore they break validity. But there is an alternative translation that can be designed that embed LK into LL and can be lifted to μLK and μLL, and that does not introduce cuts. And from this, we can obtain the cut elimination result, and also that we have productive cut reduction strategy for mLK and μLJ infinite, sorry, because there is a notion of a skeleton of an intuitionistic and of the linear decoration of an intuitionistic proof and an LL proof, so that we have actually not only cut admissibility but really productiveness of cut reduction strategy. So then my opening will be really short openings. So how much time do I have? Do I have 5 minutes? 5 minutes, yes. And then that leaves 5 minutes for questions too. Yeah, okay. So so to go quickly about this notion of bouncing thread, actually we can have non-well-founded derivation containing cuts and containing infinitely many cuts, but still there are cases where we lose validity for a reason which may seem a bit odd. If you consider this derivation, here I have a cut on a cycle. So that means on the infinite branch here, I will have infinitely many occurrences of this cut. And if we try to build a thread, we won't be able to build an infinite thread because every thread on mu will go, when it encounters cut, will go to the left and die in an axiom. So on the right branch, which is the infinite one, we cannot have an infinite thread. But still, this proof has a very productive cut elimination. And there is a way to restore and extract threads from this proof, which is actually to connect threads through axioms and cuts in a way which is familiar to geometry of interaction. And that's what we call bouncing validity. So you can imagine how to, that we have like those threads that can move up, bounce on an axiom, move down till a cut, and then continue. And we'll say that a proof is valid if it contains a bouncing thread where the new unfolding are all contained in the infinite branch. So I won't detail this because I have not enough time. But in that case, we have soundness and cut elimination for this extended notion of non-wellfounded proof. But then the notion of decidability of criterion is still there. And actually, in general, we cannot decide bouncing validity, okay, because we can reduce termination of Minsky machine to bouncing validity checking. So that's an issue. But still, the result we have is that there is a hierarchy of decidable conditions that approximate bouncing validity, in the sense that each time you bind if you bound the height of a cut, then you get decidability again. So the BK valid proof is a bouncing valid proof such that the size of bounces is less than K. And what is important is that every bouncing valid circular proof is BK valid for some K. So this hierarchy actually captures all bouncing valid circular proofs. So this is decidable, and it gives us a semi-decidability property for bouncing validity. So in this way, we have a hierarchy of validity condition. Okay, so cut-free valid pre-proofs, the straight valid pre-proof where thread only moves up, then the various BK valid proof that approximate the bouncing valid proof, and then and here we are in some position where we lose decidability. So we cannot decide this green circle here. The white circle is the productive pre-proof, but so there may be more pre-proofs. Some of them should not be considered as valid logically, but they can still produce. And on top, you have any pre-proof, which may even not be productive, as the one we had in the very early slides. So this I won't detail it, but just telling you that there is a mismatch between the fact that threads only speak about the progress along formulas, while we have to state them for sequence derivation. And there are strange phenomena occurring in the sequent calculus. Typically, if you look at those two proofs, they only differ by the ordering of the nu and mu unfolding here. And the left proof is non-productive. The cut elimination will not produce a cut-free proof, while the right one is productive. So here we are in a situation of a deadlock on the left, while the computation on the right works very well. So of course, none of these is valid for the B validity condition I mentioned before, because it ensures cut elimination. And it's precisely because this nu here is outside the infinite branch. These two nus are outside the infinite branch. So natural direction, which we are working on with Abhishek Dey and Luc Pellissier for some time, is to design parallel proof objects in linear logic, and they are known as proof nets. So we have designed proof nets for mMALL infinite. So I will just review the results that we have here. Okay, so we have a notion of non-well-founded proof structure with a correctness condition that ensure sequentialization. So The correct non-wellfounded proof structure are known as infinites, and they can be sequentialized, and every proof desequentialized to an infinite. And if a non-wellfounded proof structure is an infinite, correct infinite, then we have cut elimination. So fair reduction sequence converge, but so we have to design an appropriate cut reduction using the notion of kingdom, which is well known from the linear logic proofnet literature. And I'm done with the conclusion slide. So I told you about fixed point logic, extended linear logic with finite proofs, with circular proof, or with non-well-founded proofs, and reviewed several syntactic cut elimination results for multiplicative additive linear logic, full linear logic, intuitionistic or classical logic, and proof nets. I also told you about those more expressive validity conditions, which have, of course, a very, very high complexity, but we are not in a direction of proof construction. We are really in a direction of computing with proof. So those the validity here shall be viewed as a certificate of termination of the computation. So you have to get it, and then you can run your program. And actually, the complexity is similar to the one of well-known termination techniques for recursive programs, like a size change termination. And here, let me review some. The proof nets that we are designing are still an ongoing work, in the sense that we need to design an appropriate notion of circular proof nets. And the notion of circularity in proofnet is inherently different from the one in the sequent calculus. And that this, you can understand this easily, because the notion of being a circular proof is not stable by permutation of inferences. Or if you take a strong enough notion of permutation of inference, circularity is not preserved by this notion. So direction of future work on infinites, the equivalence between the circular fragment of mMALL and mMALL, and also the same question for mULL, translating infinite proof to finite ones, but also trying to do this, preserving the computational contents. So can we, if we can finitize, is it possible also to find a notion of preservation of denotation of the proof, let's say? And finally, two direction, extend circular proof to natural deduction and lambda calculus, and not only stay with sequent calculus. And the work on proofnet is also a basis for this in this direction. And study provability and denotational semantics for circular proof, so which is ongoing work with Abhishek for probability semantics, and Tomarer and Farzad Jafaramani for denotational semantics of circular proofs. Thank you.